Okay, I assume everybody can see us. Welcome to our colloquium for this week. It is my great pleasure to introduce our speaker this week, Professor Ali Yazdani from Princeton University. We're really happy to have him because we had him here many years ago and we've been trying to get him back. And it's, I guess, it has something to do with the uncertainty principle. We haven't been able to quantum confine him until right now. So it's great that he's taking the time to really tell us about the latest thing he's doing. And by the way, he's the expert in what's, in some sense, the visualization of quantum matter using this very, very powerful technique, which he's helped to mature and applying it to a range of materials and material systems. And just give you an introduction on his background, he did his undergraduate at UC Berkeley, and then he went to do his PhD at Stanford University. And after that, he picked up this technique of standing tunneling spectroscopy, microscopy at Almaden Labs in IBM under the guru of the field at that time, Don Eigler. And from there, he went and became faculty at the University of Illinois at Urbana-Champaign. And he stayed there until 2005 when he moved to Princeton University, where he's ever been since. He's been since. His lab, which I haven't yet had the pleasure of visiting, I heard is extremely impressive. It's literally, a major outfit, probably part of an entire building. And everything is sort of dug in to be able to achieve the kind of resolutions and stability that you will see in some of the images you will show us. Now, some of the things, the awards and distinctions that's worth mentioning are, he's currently the director of the Princeton Center for Complex Materials. And he's also a fellow of the American Physical Society, the APS, and as well as the American Association for Advancement of Sciences, AAS. And more importantly, he's a member of the National Academy of Sciences in the US. So anyway, without further ado, because he's got a lot of exciting stuff to show us about this new system of twisted graphene and etc., I will just let Professor Yazdani take it over. And so we have a very warm welcome to Ali. And I will try not to interrupt him, meaning if you have questions and so forth, please hit the chat. Unless it's something important, I will defer all the questions and answers till the end of this lecture. And so please try to, feel free to chime in and I will rejoin you guys at the end. So thank you very much, Ali. Please take over.
Thank you very much, John. It's a great pleasure to be here. Too bad we couldn't do this in person. It would be very nice to visit you again in Toronto and see you all in person, hopefully soon. I'm very excited today to tell you about some of the work that my group has been doing on this new electronic system that has been quite exciting in condensed matter physics over the last 2 years. The systems associated with Moiré flat bands, which I'll explain to you what they are. What's exciting about this system is that, in a sense, it brings together two of the pillars that we often associate with quantum condensed matter physics. Of course, we think about electronic systems in which they show exotic behavior, such as high temperature superconductivity or spin liquid or Mott insulators. Many of these material systems, which have dominated condensed matter physics for the last 30 years or so, involve strong interactions between the electrons. And at the same time, in the last 10 years, the early work of discoveries of quantum Hall effect and fractional quantum Hall effect that came in condensed matter physics in the 80s, in the last decade or so, we have seen the advent of application of concept of topology in condensed matter system. And topology of the electronic bands is one in which has given us topological insulators and topological semimetals and also studies of topological superconductors. So what I want to show you today is an electronic system that actually seems to show both of these type of physics in it. So it actually brings together a lot of the concepts that we have worked on for the last 20, 30 years in a variety of different materials in what I will show you to be atomically very pristine and novel and simple, chemically clean atomic system. So all of this excitement came about in 2018 by discovery by Pablo Javier Herrero, which I'll highlight in a moment, by studying basically what happens if you take two layers of graphene and put them on top of one another and twist them relative to one another. So remember, the graphene has this hexagonal atomic structure, and we think about the atomic sites in this graphene as the two in equivalent location, the A and the sub and B sublattice location on the graphene atomic structure. And what you're picking up here with your eyes is the way in which the atoms on the top layer and the bottom layer are registered relative to one another. And by twisting this structure, you get this long wavelength Moiré superlattice structure, the periodicity of which is very sensitively dependent on the angle between the two graphene systems. So in a sense, what you have here is you're subjecting electrons that are moving in the graphene sheet to a new periodicity, to a longer periodicity than the atomic structure. And that changes the band of this system, the electronic bands. So let's look at how that happens. And this is actually what motivated much of the work in this field. It came from early work by Bitzidrer and McDonald, which they theoretically looked at this problem of twisting two bilayers of graphene on top of one another. So remember, graphene has this Dirac-like electronic band structure, which is what is shown here on the left. And we also in condensed matter not only think about basically energy versus momentum, we also think about what the Brillouin zone of the system looks like. And this is the Brillouin zone of the two graphene sheets basically placed on top of one another. These blue and red points are the Dirac points that are now, of course, rotated relative to one another when you rotate the two graphene sheets relative to one another. Now, as these authors did, they consider what will happen if you start to electronically couple the two graphene sheets together. So you start to hybridize the electronic states from one graphene sheet in blue to the other graphene sheets in red, which is sitting on top of it. So what happens is that if you consider this interlayer interaction, is you of course start to modify the band structure. So the simplest way to see what happens here that's exciting is to think about the bands that are coming out of the Dirac point and where they start to overlap. Basically, the interlayer interaction starts to open up, if you like, a hybridization gap here. And as a result, what happens is that the resulting band that's emerging, it starts to kind of be pushed down relative to where the Dirac point is. And what theoretically was shown was that as you decrease the twist angle, essentially what you get is a condition in which this hybridization becomes such that it becomes comparable to what the Fermi velocity of the system is times the momentum of the Dirac points. And essentially this point gets pushed further and further down below. So this is a very interesting situation because what happens is you start with these highly dispersive bands, and what you get because of the interaction between these two layers, you result in what we call a very flat band. And it was shown that there is a magic angle around 1 degree where you get the flattest band condition that you observe. And if you like, the Fermi velocity of the electrons in this system at the chemical potential, at the Dirac point, at the charge neutrality point, would go to 0. So let me show you this in some animation that actually comes from Pablo's paper. This is basically showing you the Brillouin zone, the electronic bands of the system as you start to twist them. And right about here, around 1 degree, you see that the system gets into a very flat band condition. So the electrons are basically living, if you can put their chemical potential into this band, all at very much the same energy. And this is a recipe, as it was already pointed out in the original papers, for a really strong electronic interaction, okay? And of course, let me give you a little bit more detail because this is a way in which we need to understand the system. So of course, we have to consider how the layers of graphene relax as you rotate them relative to one another structurally. And if you include all that, again, if you think about the energy of the electrons as a function of their momentum, you have what we call these flat bands. But of course, these flat bands have spin degrees of freedom, which we know, but also they have what we call valley degree of freedom. In graphene, there are two valleys, the A and B sublattice structure in the graphene sheet give you another degree of freedom called valleys. And when you fill electrons in the system, you can basically have up to 8 electrons if you like, occupying these two flat bands. So you have two bands, two spin, and two valleys. So that's a picture in momentum space. We can also think about what would the electrons look like if you look at their wave function in real space, their density of states, where they are located in real space. Of course, what we are most interested in are the electrons living inside this flat band. And what you find from theory is that what you would expect to see is that the electrons are basically have their wave function being, the density of state being maximal over the sites which are called, I call the AA sublattice, so which is orientation. So you have the A sublattice from the top graphene sheet is sitting on top of the A sublattice in the bottom graphene sheet. And at those locations of the Moiré superstructure in this system, you have kind of like where the electrons would like to sit. So which is what this is kind of what we call the Moiré sort of the superstructure in this system. You can think about this Moiré superstructure of the system as its own lattice, which is sitting on these AA sites. And if you like, the way I like to think about it is each of these sites can take up to 8 electrons. Now, this system is actually slightly even more complicated, and this is where topology comes in. Remember, we are starting from the Dirac point of the graphene sheets when we construct this system. Now, the Dirac point of graphene has associated with it what we call the Barry curvature around the Dirac point. And this Barry curvature is something that will become important later as I discuss the topological properties of the system. So, of course, all of that is sort of in theory. And of course, what got everybody's attention was Pablo's work in discovering that when you partially occupy the electronic bands, the flat bands of this system, you get a very exciting behavior where you get electrons first to show an insulating behavior in a partially filled band, which is telling you that this system is some sort of a correlated insulator. Initially, this was thought to be maybe a Mott insulator, which I'll talk about as we go along here. But more exciting than that is the idea that if you dope this system away from the Mott insulating phase, the system shows superconductivity, which is occurring very close to an insulating phase. Of course, for those of us who worked on correlated superconductors, this became very exciting, and this is one of the reasons we jumped into this field, because the electronic phase diagram of the phases that you observe in this system as a function of temperature and carrier density looks a lot like what we see in high TC superconductors or other correlated systems. In fact, you just need to sort of flip the diagram of the high TC one to see that when we basically start with a Mott insulator there and dope it, we get a whole dope superconductor. And here we have sort of domes of superconductivity near this insulating phase. So of course, this is very exciting. And initially, of course, the question is, well, maybe this is a very similar phenomena. And what's nice about this material system, as I will show you today, is allows us to do experiments that were basically impossible to do in these correlated superconductors. In a single device, like Pablo's experiment here, we can tune between many different phases. And as I will show you, we can do experiments in which we can go beyond this sort of impressionistic correlation between what we see in this system and high TC superconductors, but actually experimentally show that this is a strongly correlated system. So what's exciting about that is that it's giving us a new platform. And this is kind of the more general perspective. We usually typically think about modifying material chemistry to tune electronic correlation in materials, like by changing the elements or the structure of the material. These systems are so complicated that we are relying on, for example, understanding from cold atoms and optical lattices to give us guidance to think about how correlations give rise to different phases in these complicated materials. So in sort of a broader perspective, I think these Moiré systems is giving us a new type of electronic platform, one which is atomically can be pristine. You can have perfect, basically, sheets of graphene with almost no defects, and in which you can have a chemically very pristine and not disordered system in which you can study electronic correlations. And I think in addition, if that wasn't enough, then there was a discovery that this system can also show some topological property. This came from the work of David Gordon and Andrea Young at Stanford and UCSB, where they showed that when they took this twisted bilayer graphene, and typically, as I show you, we construct these systems on top of a boron nitride layer underneath it. When they align these things together, lo and behold, this system shows what we call the intrinsic quantum anomalous Hall effect. So you're familiar with the Hall effect, which can be quantized. Anomalous Hall effect is a system in which you can use the magnetic field to train the system into a quantized Hall state, but remove the magnetic field, and a zero magnetic field, the system should show quantized Hall conductance. So this is a topological phase. And as I'll show you, we have now discovered actually new and unexpected topological phases in this material, not just from alignment, as is shown in these experiments, but because of the strong correlation in the system. So I'll show you that towards the end of my talk. So as a way of concluding this introduction, this is a material system which has resemblance to what we call correlated materials with like Hubbard-like physics, where you have electron localization and strong interaction between the electrons, but it also has some connection to topological system like we are familiar with in the quantum Hall systems. So the flat bands of this system can kind of be thought about maybe in both of these pictures, which makes it actually very interesting. Okay. So as John mentioned, what my group does is we use the scanning tunneling microscope to study all kinds of electronic material systems. And we've been working, of course, on topological system, but going back to high TC and also other correlated superconductors. So when this correlated system came along, we started to think about how we can contribute. So what I want to show you today is I'll show you how we use the scanning tunneling microscope, which I'll explain how it works in a second, to explore these graphene Moiré devices at the magic angle. And I'll show you how we use the spectroscopy in this system to actually show how we can go from single particle physics to many body physics in a device, and how we probe that experimentally, and how we demonstrate that this is a strongly correlated system. I'll show you how the relationship between these and maybe the insulating and the superconducting phases of the material. And if there is time towards the end, I'll show you how we actually have used the STM to develop a new technique to detect correlated topological phases and have found something very unexpected in this system. So let me remind you how an STM works. It's a sharp metallic tip, which you bring near the surface of the material, which you have freshly prepared. In its imaging mode, the electron tunnel between the tip and the sample. And when you raster it across, you keep the tunneling current constant. And following that trajectory, the STM images give you the contours of constant electron density of state in the system. It's a way to image the atomic structure, but also through the electronic density of states in the material. At every location on this in this measurement, we can stop the motion of the tip. We can open this feedback loop, which adjusts the tip height and keeps the turn constant, and measure the tunneling rate as a function of the voltage between the tip and the sample. This allows us to measure the density of states. So this is a conductance between the tip and the sample as a function of the voltage between the tip and the sample. And this gives us the density of electronic states as a function of energy of the electrons in the sample, 0 being the chemical potential. Of course, being a scanning tool, we can perform this experiment as a function of position and build maps of what the electronic states of the sample, if you like, the square of the wave function of the electrons in the sample surface, look like as a function of location. Even before the discovery of twisted bilayer graphene, our group was starting to transition into studying 2D materials because the ability to have an electronic system in which you can tune its density with a gate, and this is sort of the advent of 2D material has made this possible, it makes it very exciting for us to do a new kind of experiment, which we hadn't done before. So this is what I call density-dependent spectroscopy, where we tune the electronic density where the chemical potential is in the system and probe how electronic property of the system changes as a function of the density of the electrons. As I'll show you, this gives us a very powerful way to actually study the system, in particular twisted bilayer graphene, when the electrons are strongly interacting and when they're not, by just tuning the chemical potential. So how do we do this experiment? So our transport colleagues who developed these systems have developed the techniques for creating these 2D devices. Just to make a short familiarity to this, the way this works is you're basically using a polymer a stamping method to pick up 2D materials which you have created using basically Scotch tape on a silicon surface, and you sequentially pick up different 2D materials. You may tear some apart, like the monolayer graphene, to create 2 layers of graphene at a different angle stacked on top of one another. And of course, this is what our transport colleagues have developed. That's how you make these 2D devices. But for us doing STM, we have to create, we have to turn this upside down, and we also have to create very clean surfaces. And this has been an unusual challenge because, you know, in these processes that you see here, it involves using fabrication, using polymer stamping, using solvents, and all of these things pose a very big challenge to create devices which are atomically clean, and then you'd want to do STM measurements on. So a lot of progress have been made by our group over the last 2 years to start to make atomically pristine devices of these Moiré systems. And here's the Magic Angle Twisted Bilayer Graphene device. And so here's an STM image. And now right away from this image, you can sort of see it tells you a lot of pieces of information. So at the finer scale, which is hard to see, are the carbon atoms of the top graphene sheet. That's what your eyes are picking up. Then you sort of see at the larger scale these bright spots, which is its own hexagonal lattice. As I told you, when we are thinking about the flat bands of this system, that's what gives rise to a large density of states at these locations. So this is the Moiré periodicity of the system, having to do with the 2 graphene sheets that are twisted at around 1 degree relative to one another. From STM measurement, by basically measuring this periodicity, we can extract basically what angle our sample is that's being constructed at. And this is kind of a guessing work in other experiments, but here we can measure it experimentally. The other thing you see is an intermediate length scale in this image. And that actually has to do with how these twisted bilayer graphene, which is almost aligned with each other, they're just 1 degree off, how are they aligned with the boron nitride layer underneath them, which supports them? The boron nitride is placed there in order to basically separate this from the substrate underneath to not give rise to fluctuations of charge that will screw up basically what we will want to have a pristine electronic system. As I mentioned, that's kind of an important factor on how this system behaves. And here we can also characterize that angle from these images. We can also use these images to characterize strain in the material. And that is something that plays a role, which is very hard to look at from any other technique other than these imaging techniques such as STM. Okay, so this is what our device looks like. It looks a lot like what our colleagues have found exciting superconducting correlated insulator phases in it. Now what we can do is we can start tuning the gate and start matching the conditions where these other phases have been discovered and try to see what the electronic properties of the system looks like. So let me start with what I call very large negative or positive gate voltages in this device. What this gate voltage does is completely depletes or completely fills the 8 electrons from all of these Moiré sites. That's a way to think about it. Now, if you put your STM tip on top of one of those bright spots and measure the tunneling rate as a function of the energy or of the electrons going into the sample, which is tuned by tip sample bias, you see 2 very sharp peaks. And these 2 sharp peaks are associated with the 2 flat bands. It's the Van Hoos singularity associated with these electronic bands that are very flat. They have very little dispersion, so they just show up as a very sharp peak in these
density of state spectra. You can see that the two sharp peaks can be below 0 and the two sharp peaks can be above 0. So, and this is basically telling you that when we are in the non-interacting limit of the system, when these bands are completely filled or they're completely empty, they kind of match our expectation of having produced flat electronic bands. Now, what's even interesting is that we can match the shape of these spectra, or try to understand the shape of these spectra, some of the details and other features of other energies, if we include not only just the angle of the device we have made, but also even the strain that we can extract from these STM images into the theory of the band structure theory of the system. And when we do that, we can basically start to understand the single particle physics of this system very accurately. So we have a very good handle on the electronic bands in the system coming from the region where you have either fully occupied or fully emptied these flat bands, where single particle physics should be working very well. So let me show you the first thing we discovered. So I'm going from those spectra that were two peaks to show you data in a slightly different way. So here on this panel on the left, what I'm showing you is on the y-axis is the gate voltage, which tunes, as you see, the number of electrons inside this Moiré superlattice structure. 0 is the charge neutrality point. We can deplete the 4 electrons that are there. We'll go to -4, or we can add 4 extra more electrons there to +4. So this is a filling factor is an important thing to is the important parameter in this system. So what I showed you so far is when we are at above +4 or below -4, is the system shows 2 very sharp peaks that you see in this panel. And that goes over in this panel as two lines, 2 almost parallel lines that come in and they suddenly jump and the system changes as you start to partially fill the Moiré electronic structure, as you go between +4 and -4. So what you see is those sharp features in these measurements become extremely broad as you go in the intermediate fillings. So there's a lot of data on this panel, on this slide, but what I want you to focus on is some very simple features. One is the panel on the right here shows basically the sharp peaks, and those sharp peaks are basically present when you go all the way to the right panel when the 2 flat bands are completely unoccupied. So that's what I told you before. And what you see in the middle is all this broadening. There's of course additional features which I'll get into in a second. You see all this broadening of the electronic density of states of the system. So instead of the electronic levels of the system being sharp in energy as they were when they were fully occupied or fully emptied, somehow our measurement starts to show these very broadening features, which is very unusual. So these are signatures of the breakdown of single particle picture of this highly interacting system. And let me tell you, where does that come from? So let's abstract this problem to a simpler problem. So of course, there are these flat bands and they have dispersion. Let's just think of 2 energy levels and think about where do these electrons live? These electrons basically live in this Moiré superlattice structure. So in a sense, you can think of them as a bunch of quantum dots or atomic levels that are living in these Moiré sites. And they have their dispersion is very flat, which means the hopping between these sites is very weak. So let's consider how you would probe this system if you try to add or remove electrons from it. Well, what the mean field theory will tell you is that, well, if you have basically the 2 levels and there are nothing occupied in either level, and let's forget about the spin and the valley degeneracy for a moment, you can put your electrons in the lower level or the upper level and you just should get 2 peaks. And those 2 peaks would be broadened by whatever is the tunneling rate between these sites. Now, if you add 1 electron, you would say, oh, then of course I have to pay the Coulomb energy if I want to add an additional electron to the system. So the next energy level in this system, so I'm assuming that you can only put 1 electron in each level for now. The next electron will go to the upper level and you have to pay the Coulomb energy U. So this is all nice and fine. But the problem is that, of course, electrons are not, now we are interested in partial occupancy. So if you partially occupy this level, the mean field theory would say, oh, just adjust your expectation of what the energy is for the next electron to go in by the probability that that level is occupied. But the problem with mean field is that, electrons don't come in fractions. You have to either occupy that state or not. So in reality, what the mean field theory is doing is averaging two things, is averaging the probability of the electron being there, which gives you an energy level for the next electron arriving at E plus U, or an electron not being there, and you being able to put the next electron in the energy level of the next level. So what a mean field theory is doing is ignoring all these fluctuating states, these charge fluctuating states, by just replacing them with their average. So the first indication of strong correlation in the system is these broadenings that we see in the experiment I showed you here. This broadening basically indicates you can go and try to make a more exact model of these, which is very difficult, as I'll explain as we go here. But just the broadening fact itself is basically indicative of this physics of the breakdown of this mean field picture, where you cannot replace this picture with its average. So we can think about the broadening as being many different charge configurations that the system has, because the electrons are very strongly interacting with one another. And when you try to put the next electron in, you're seeing all those charge fluctuations. So we have done also some exact diagonalization, as I'll mention, with our colleagues, to actually with the extended Hubbard model that shows features like we see in our experiment. And this was sort of the first work that we did in this field. So this was a bit, I would say, qualitative. Then we started to notice more quantitative features in the data. So if you look carefully in this region in the middle is where all the blare is, right? And this blurry region, and let me also indicate we are starting at temperatures before we get to the superconducting phase and before we get down to the insulating phase at low temperature. It's in this blurry region, which is all the interesting physics happen when you partially occupy these flat bands. So if you look carefully at these blurry regions, you can sort of see that there are additional features that are happening every quarter filling in the system. So every time we go from 4 to 3 to 2 to 1 and -1 and -2, there are features in the data that seems to repeat themselves. So let me bring them out. And the way we bring them out is plot the data in a slightly different way. The difference is that we usually just look at conductance of the rate of tunneling. But if we normalize the rate of tunneling by the conductance that we have in the junction, we basically take out the fact that these measurements are done at many different tip heights. And this is one of the technical things that's important. But if we remove that, you can sort of more clearly see the cascade of transitions that are happening in the electronic property of the system every time you go through a quarter of the filling. So what are these features? So this is a very complicated many-body problem. You have a flat band. So let's ignore the bands for the moment and just replace them with levels at each site. Well, of course, there's some hopping that gives you the bandwidth. And of course, there are 2 spin degrees of freedom, and there are 2, what I told you, Valley degrees of freedom. So the full many-body problem of electrons in this system is even more complicated than cuprates, because you have all these degeneracies having to do with the spin and the Valley degrees of freedom of this electronic system. So how can we make progress? Well, again, we make the simplest sort of assumptions to try to see if we can get the data or understand the data. And the simplest assumption we can make is we can just view this system as sort of an isolated, sort of very weakly coupled dots. We think of this as what we call the infinite U Hubbard model. So just ignore the hopping. And we borrow this idea basically from the STM images themselves. The STM images tell us that there are these bright spots. And think about those bright spots as where electrons are mostly living. And think of them as being in 2 levels, the flat bands. and think of them as repelling one another on an energy scale that needs to be determined. And we can try to make a go at trying to understand how the spin and Valley degrees of freedom modifies what you would measure in an experiment like us. So that simple model, very simple model, actually can go a long way to try to understand what we are seeing in the STM images. So what I've shown here on the left panel is a calculation that comes from that infinite U Hubbard model. And you can kind of think about this as just a quantum dot with basically 2 levels, and each one of them having degeneracy of 4. And what you're asking to do in the calculation is ask, when can I add an electron to the system and at what energy? And when I can add an electron, you basically get the large signal in the panel on the left. You can clearly see the resemblance to the experimental data. You notice that the features that you see here is rather sharp. You know, there are like very rapid transitions as you go through each of the quarter fillings. And the data doesn't have those rapid transitions. And we have extended this sort of simple model with some exact diagonalization with very small clusters of 6 or 7 sites. And we've convinced ourselves that these sharp features develop sort of more broadening, like you see in the experimental data. But what's interesting and instructive about doing this comparison to this simple model is that it allows us to read off some features that we put in the model, like the repulsion between the electrons. And of course, we know something about the energy spacing between the 2 flat bands from the experiments. And if we put that in the model, we can convince ourselves that the features that we are seeing having to do with basically a Coulomb repulsion in the system, which is of the order of 23 millielectron volt. Now you might say, why is that number important? The reason that number is important is that number is probably about twice the bandwidth of the electrons in this system. So you have these very flat energy levels, these flat bands, and the strength of the interaction between the electrons when they're in these flat bands exceeds the bandwidth. And this is a classic situation for having very strong correlation. So this is an experiment which quantitatively measures the interaction strength of the electrons in this system. So it's a very large number, 23 millielectron volt, compared to the bandwidth of this electronic system. Now you might ask, what are these features that you're attributing to the data? I won't go through the details of this, but these are all the ways in which you can add or remove electrons. And the reason the features shift around in energy and they have transitions as you go through each of these fillings of these bands, it has to do with the fact that the degeneracy of this system is quite rich. And I would skip the details of explaining where all these features come from. But what's the consequence of this? So the consequence of this is that our transport colleagues have shown that when they cool this system down, the system starts to develop superconducting or correlated insulating phases. In fact, there are some very nice data from Dimitri Efetov from Barcelona, which shows that there are correlated insulating phases at every integer filling in this system. And near those correlated insulating phases, you get superconductivity. So the experiments I showed you so far were at higher temperatures than all this sort of ground state physics. So what we are finding is that the system with its very large U is basically looking at polarizing these Hubbard sub-bands as you cool it down. And this polarization of the Hubbard sub-bands is probably what's behind the formation of all these correlated insulating phases. And what our experiments suggest, although we haven't probed this yet, and this is something that is not really clear at all the correlated insulating phases, is that there are possibly spin or valley polarized states that are forming when you're at integer filling in this system. And the transitions that we see between these integer filling in our experiment is indicative that that's where the system is headed. Okay, so I talked about where is the system headed as you cool it down? And of course, there are the insulating phases, which we don't know much about, except we know that they do form gaps at the chemical potential, just like any insulators you would expect to see. And we can detect these gaps at very low temperatures. So what's shown on this slide is what I've been showing you so far, but not cooled down. Electrons are cooled down to 200 millikelvin. Some of the features get very sharp, and I don't want to focus on everything, but I want to focus on a couple of interesting things, which is the most interesting aspect of the electronic property of this system. So going to what we know from the transport studies, we know that when we go from charge neutrality of this system and deplete 2 electrons out of the system, we get a correlated insulating phase. And then when we deplete more electrons out of it, we hole dope it more, the system shows superconductivity. So what we have found is we can very nicely see this insulating phase. Actually, we see it very sharply in our STM studies. So what the color scale here represents is a suppression of electronic density of state. And this suppression that you see where my cursor is near nu equals -2 is a formation of an insulating phase very sharply near that filling. And what's nice in the data is that you can sort of see this state, the electrons forming one gap, and then that gap closes, and another gap opens up, and it extends almost all the way to nu equals -3 and beyond. So this is quite tantalizing for us because this looks a lot like we are now probing the physics of the ground state, and we can ask some detailed questions. And these are some preliminary data in terms of trying to understand what the ground state properties of the system is. So here I show you the same data at high temperature, cool down to low temperature. The system develops an insulator and another phase which is gapped. And when it's insulating, you can do the measurement and you can see something that looks like not a fully formed gap. And what's interesting is that this gap closes and there is a transition, and the system transitions into another phase which has a very tantalizing gap that looks V-shaped. So why is this interesting? Well, with this same instrument, we can put a piece of aluminum, and aluminum actually has the same TC as this system, is about 1 Kelvin. That's when superconductivity is detected in this material. And you can clearly see that we have very nice resolution to resolve the shape of aluminum spectra, which is what it looks like is basically like a classic BCS superconductor. So what's interesting from this preliminary data is that this doesn't look like your garden variety superconductor in its spectroscopic property of the gap. So, so far we have established basically not just the fact that this system is a strongly correlated system from the measurement of the spectra at high temperature, but from that soup of the strongly correlated system comes a superconducting phase, which lives near this interesting insulating phase, which has a very unusual and not BCS-like superconducting gap. So let's see. So how am I doing on time?
6 minutes.
6 minutes. Okay.
Regulation time. Yeah.
Regulation time. So I try to go maybe
keep going. Yeah.
10 minutes. And so I'm going to switch gears a little bit and show you some of the most recent data from the lab. And I'll try to keep this at the higher level. But it's exciting because what we have been able to see as we study the system at very low temperature near these insulating phases, we begin to also see that we can see signature of topological phases, which what's exciting about them is they appear to be both correlated and topological. So this is unique because the examples of systems which show topological phases caused by interactions is of course very rare. So we know, of course, the fractional quantum Hall phases that occurs at very high magnetic field. Those occur because of strong interactions. But all the topological phases that we've discovered so far since then in topological insulator and so on, these are mostly systems that are driven by single particle physics, band structure, and spin orbit coupling. So I already showed you the discovery by David Goba, Hubbard Gordon, and Andrea Young, which gave us this intrinsic quantum anomalous Hall effect. And the reason this occurs in samples where you have aligned your sample with the graphene, with the boron nitride layer underneath, is that there is a single particle effect, which the presence of the boron nitride, which has the boron and nitrogen atoms being, of course, different, they produce a potential on the graphene sublattice on the A and the B sublattice sites, which is different due to the presence of boron and nitride underneath. What this does is it takes the Dirac points of the system and gap it. And this gapping is a single particle effect. And this introduces for us a condition which, of course, interaction seems to play a role, but a weaker role in order to create these phases where you have anomalous Hall effect. So you might ask, okay, you're doing a spectroscopy measurement when you talk about Hall conductance and detecting a quantum Hall effect or fractional quantum Hall or anomalous Hall effect. How could you measure that using an SDM? So this is something that my students came up with, and I'm very proud of them, that they realized something very interesting from making measurements in a magnetic field, which is what you use to measure the Hall effect, and also varying the density of the system. So if you combine our relationship for a quantized Hall effect, which has, of course, the value of the quantum Hall, and of course, it has a number C, which is our Chern number, associated with what kind of topological phase you have. If you combine that relationship with Maxwell's equation and Ohm's law and charge continuity, as Strada did in the 80s, you arrive at a relationship which relates how the density of the system and the magnetic field changes as you tune those systems if you are in a topological phase with a Chern number. So what does this relationship mean? What this relationship means is that if you apply the magnetic field and if you had the density at which the system becomes an insulator, and if that insulator is a topological insulator, if you varied the magnetic field, you have to adjust the density of the system to keep the system in the same insulating phase. And the rate at which you have to do this variation depends directly on the Chern number that appears in the Hall conductance. So this basically gives us a tool, as a new spectroscopic tool, which we can use. It's kind of like a Landau fan diagram for those of you who are familiar with it. It gives us a spectroscopic tool with the STM, which I'll show you in a minute. It's actually a bit more powerful than just making a Landau fan diagram to extract the quantized Hall conductance. So I know this looks very busy, but essentially what I want you to see is that what I've been showing you, as you apply a magnetic field, the system develops a lot of features in our experiments. And the only thing I want to emphasize in these features are these gaps in the spectra that happens at the chemical potential, okay? And these gaps appear when you start to apply a small amount of field, and they seem to move around as depending on what gate voltage they appear, at what electron filling they appear when you adjust the density of the system. So these are these gaps that I want to follow. So to make a long story short, what we do in the experiment is we vary the gate voltage and we vary magnetic field, and we measure gate voltages at which we detect gaps. And we follow them as we change the magnetic field. And these lines basically indicate how the field dependence and the density dependence of this gap, which is directly related to what this formula is trying to tell us to do in order to detect whether these gaps are topological or not. And what we discovered is that this system has a sequence of topological phases, which are basically starting out as you start filling electrons from 0 to 1, 2, 3, 4. These are these topological phases that is just completely unexpected that comes in this system. So let me let me go back. Yeah, so we have done this experiment on now many devices. I don't have the final plot in this figure, but where we can reproduce these slope lines for many devices to confirm them. And what's exciting is that these insulating phases are not just your garden variety topological insulator because of some band structure physics. These are formed because of interactions. And the reason we know that is that the gaps that support the formation of these states occurs just at the chemical potential. And if you change the gate voltage, which changes the density of the system, these gaps basically disappear. At the right filling of electrons, the system spontaneously basically starts to form these Chern insulating phases. Their presence seems to need applications of small amount of magnetic field. And this is something that basically now a number of different groups, since we came up with these experiments, and we realized that there were several other groups were working exactly on the same measurements, except using electrical transport studies. And they have also produced the signature of these Chern insulating phases. But what's exciting about the STM results is that it shows that these Chern insulating phases have gaps that are only at the chemical potential and therefore are created by the strong correlation in the system. Now, I think I've run out of time, so I think I won't dwell on how we understand how correlation introduced these states, just to say that we think that strong correlation gives rise to, with a small amount of field, spontaneously breaks time reversal symmetry in this system, and it gaps the Dirac point, and it creates these Chern phases. And the reason it's exciting is simply because we believe that there is a connection between these Chern insulators and their magnetism being unusual. They're likely orbital ferromagnets, which are forming because of the fact that this system has valid degrees of freedom. And these are these Chern insulating phases that we are detecting in our experiments. So they're very unusual correlated phases, which are created by the presence of strong interaction in this system, breaking basically the time reversal symmetry spontaneously and forming these orbital magnets. So let me conclude. So what I want your takeaway message to be is that these 2D materials provide a very interesting opportunity. In fact, let me go to the next slide and come back to my conclusion. There is a very large number of 2D materials that are being twisted on top of one another, and they provide a very wide platform for studying electronic correlation. And I think that with this example that I showed you, we see that Coulomb repulsion is probably the largest electronic energy scale when you are at the magic angle. And it creates novel states, not just a superconducting one, but these unusual Chern insulating phases. So before I close, let me just tell you who's done all the work. This is a work that got started in my lab by Younglong and Berthold soon after Jiaming Liu joined our group as a postdoc. And we have now a large group of people working on this Moiré system. The work that I showed you mostly responsible for is by Dylan, Kevin, and Mongchul. And it all is possible because we could not only take the great data, but work with some great colleagues, Bial Lang and Andre Bernovic, who are the theorists here at Princeton, who've been helping us to understand these experiments and gave a lot of theoretical support to the understanding that I described to you throughout this talk. So with that, I stop and see if there are any questions.